Today we're doing an in-depth review on Battery Buggy, the 2017 to 2018 Division B event for Science Olympiad. I'd like to give credit to both Papesh and Brother Nigel, as I used some of their slideshow in my presentation. So let's get started. So what is Battery Buggy? The objective of Battery Buggy is to have a battery-powered vehicle travel a specific distance as quickly as possible and stop as close as possible to the center of a finish line. So the vehicle must be propelled by only energy from a maximum of 8 commercially available batteries. Including rechargeable batteries, they have to each be rated at 1.5 volts or less. They have to be available for inspection by the event supervisor, and lithium metal, lithium ion, and lead acid batteries are prohibited this year. They must be able to fit inside a 30 cm by 60 cm box and can be any height. It must be started by actuating a switch of some sort with a pencil supplied by the event supervisor, and you cannot hold it while doing so. It has to come to a complete stop without any outside assistance, and braking systems cannot contact the floor. Sighting and lighting devices may use electricity, and they may be placed on the track and or on the vehicle, but they have to be removed before each run. Labeled lasers are permitted, and you can see the laser policy at soink.org. A single 1/4 inch wooden dowel must be attached to the front end of the vehicle, and it has to be taller than 20 centimeters. It also must extend to within 1 centimeter of the track surface. This is a major location of a lot of construction violations on this event. The bottom front edge will be the vehicle's measurement point for distance measurements, and it cannot have any electronic components other than the electrical items listed in the rules. Batteries, wires, motors, switches, resistors, potentiometers, and mechanical relays are allowed. New this year, you have to have a practice log in which you have to have at least 10 practice runs recorded with at least 3 parameters, which have to include distance, time, and other additional parameters, such as wheel turns for braking or distance from target. So these logs will be impounded. You have to have review data. So the supervisor will review the teams and the data and penalties recorded on the score sheet. So for testing, to achieve the maximum score, the vehicle should be thoroughly tested. It should be adjustable to travel any distance from 9 to 10 meters. The distance will be in 50 centimeter intervals for regional tournaments. It will be 10 centimeters intervals for state tournaments, and it will be 1 centimeter intervals at the national tournament. It may not stray from the centerline tape. It has to come to a complete stop with the vehicle's measurement point as near to the point where the middle of the centerline tape intersects the finish tape. So this is the track. You can see the 0.5 meter line where the timing starts, the 8.5 meter line where the timer ends, the centerline tape running down through the center, and the finish line where the vehicle comes to a complete stop. And the target distance is 9 to 12 meters. So the track will be on a smooth, level, and hard surface. It will have a starting line, finish line, center line, 0.5 meter line, and 8.5 meter line marked with 1-inch tape on the floor. You could see that in the previous slide. It has to have free space to allow the buggy to stray from the centerline tape and pass the finish line. If more than one track is used, contestants may choose which track to use. Both runs, however, for one team will be on the same track. For the competition, the students will place their battery's measurement point on the starting line. They will set the buggy in motion by actuating some sort of electrical switch. They may not touch it, but must use a number 2 unsharpened pencil supplied by the event supervisor. They may use non-electric measuring devices to verify the track dimensions, but they can't use the vehicle to do so. They may place a target, which must be removed prior to starting each run, on the finish line in aid to align the buggy. They may, between runs, remove or install or change any impounded parts, including batteries. They will be allowed up to 8 minutes to adjust their battery buggy and make up to 2 runs. If a run is started before the 8 minutes is up, that run may be completed. They must wait behind the start line during the runs until called by the event supervisor. Let's go on to scoring. For each run, the judges will determine if the buggy strays from the centerline tape, the time the buggy takes to travel the target distance, the time starts when the vehicle begins forward motion, and ends when the buggy comes to a complete stop. The distance from the measuring point to the finish point. This is a point-to-point measurement. If the vehicle goes in the wrong direction, it will be considered a failed run, and it will still count as a run. If the vehicle inadvertently begins a run, it will also be considered a failed run and count as a run. If the vehicle does not move upon actuation of the switch, the students may request another try, and that attempt does not count as a run. So the run score is equal to the sum of the following. Remember that the low score wins. The distance score, this is the measured distance in centimeters to the nearest 0.1 of a centimeter. The time score is the run time to the 100th of a second. And the centerline score. If the centerline tape remains between the left and the right outside edges of the vehicle's widest axle wheels during the run between the start and the finish line, 10 points will be deducted. This vehicle may cross the finish line and still receive these points. So the run score is equal to the distance score plus the time score plus the centerline score. Ties will be broken by the first tie breaker, which is the lowest time score of the final scored run, the second tiebreaker, the lowest distance score of the final scored run, and the final score will be the lowest score of the 2 run scores. So let's go to systems, construction, suggestions, and ideas. The first issue we have is kinetic energy. So you have to do whatever you can to increase the speed of the buggy. That includes mass, wheels, whether you should have 3 or 4, the motor's strength, which is the torque or revolutions per minute, the efficiency of the energy transfer, and you have to reduce the overall friction of the buggy components. And also the battery decision, what will give you the greater voltage and therefore the faster motor. So I was found that with 4 wheels you can have a better score. I think this is because with 4 wheels you have increased traction with the ground, so you have better grip with the ground, and your wheels can be more aligned, like this. However, compared to a 3-wheel system, the front wheel does not have any axle to align it, and even if the axle was aligned, it would be quite wobbly and unstable, resulting in maybe cars that veer to the left or veer to the right. In order to reduce the friction, a good thing to use is something called a ball bearing. A ball bearing is a metal object with a hole in the center and with little balls inside it. This will reduce the friction greatly between the axles if you choose to put an axle inside, like so. So for the body and the chassis. So the body and the chassis connects all the other parts and systems together. It's probably the easiest to design and build. Remember, a Matchbox car cannot travel a straight distance for a great distance, so you should make both the wheelbase and the track as wide as the rules allow. And also, be very careful, no 2 rules are alike. Strongly consider some way to adjust the steering of your vehicle, since it's pretty difficult to get 2 axes parallel to each other. So a very simple, and probably the most efficient, frame design is just a simple rectangle. And you can make this out of wood, aluminum, or any other material that's both light and strong. So you can have your 2 axles like this, and you should make one of the axles positionable, maybe this one, so they can either move here, so to the left, or to the right, in case you did not align them properly so it will travel in a straight line. Next, let's move on to the wheels and the axles. The axles may be part of the transmission, or they can be as separate systems. Wheels are very difficult to make exactly round, so don't make them. A large diameter wheel revolves fewer times to travel a given distance. The transmission must have a higher gear ratio. The vehicle might travel faster, and it will be heavier. The smaller diameter wheel revolves more times to travel a given distance. Transmission can have a lower gear ratio, and the vehicle might travel slower and be lighter. The optimum size is somewhere in between, and both of these are affected by both the motor power and affected by the gear ratio. So wide wheels tend not to drift as much, and tend to force the vehicle to go straighter, but they do have a greater mass. So a very good formula to calculate the amount of revolutions your wheel has to make is by using the diameter formula for a circle. So if your wheel's a circle and you know the diameter, you can simply take pi, multiply it by the diameter, and get the circumference. Let's just call that cir. So then you can take the total distance traveled, divided by the circumference, to find out the number of revolutions you have to turn your wheel in order for it to travel a certain distance. Now keep in mind this might not be exact, you might have to do a couple less or a couple more, but it gives a very good interpretation. Next is the motor. The motor may be part of the electrical system or the transmission. It must be close to the total battery voltage. So motors will operate within a wide voltage range, around plus or minus 50% of the rated voltage typically, but about plus or minus 10% is better for the motor. So the revolutions per minute or the speed varies with the load and the battery voltage, and the torque or power varies with the battery voltage. Few types are available at a pretty reasonable cost. So if you have a motor that's geared in, let's say, a 2-to-1 ratio, that kind of looks like 2-to-1, and is connected to an axle, it will make this axle turn faster than the motor, but have significantly less torque. So if you have a motor that's normally spin at extremely high speed, you should gear it down, so having maybe like a 1-to-2 or 1-to-5 even, so it has enough torque to turn to move the entire car, while also having enough speed to travel very fast. So next is transmission. The transmission is probably the most difficult to design or build. It reduces the high revolutions per minute of the motor to low speeds for driving wheels. Several types are possible, including direct drive, reduction gear, worm gear, planetary gear, and a belt or pulley system, which you should avoid. They're pretty expensive to buy, and it's a definite candidate for a surplus or a salvage store near you. So a very simple gear-to-gear transmission is when you have a motor connected to a gear that's connected to another gear that's connected to the axle. Now there's different ways you can position this with the motor at a 90-degree angle. Or the thing that you should avoid is having a motor connected to a pulley system, then connected to a gear. So that you should avoid. You should either do something like this or something like this. So let's go on to the electrical system. For the batteries, the voltage should be suitable for the motor. Larger batteries last longer, but they weigh more. They evaluate different types, and the holder can be part of the chassis or a separate component. For the motor, the terminals are almost always identified in some way, such as a plus, a square, or a notch. If the motor turns in the wrong direction, you can reverse the wires connected to its terminals. Note that this only works in brushed motors, at least in the motors that I tried. So make sure your motor is brushed before you do this. The start switch should be easy to operate, should be in an accessible location, and it can be homemade. So this is a great switch to use to start the buggy. And a microswitch can be used to open the circuit at the end of the run. So what is a microswitch? A microswitch is pretty much a start switch, but instead of two terminals, it has three. So one terminal is called the normally closed, one terminal is called the normally open, one terminal is called ground. So when the button is not pressed, there will be current flowing from the ground to the normally closed. However, when the button is pressed, the normally closed will have no current running through it. Vice versa for normally opened. So if you're running a battery buggy, be sure to connect your wires to normally closed and ground. For the steering mechanism adjusts the battery buggy to travel in a straight path. Adjustment does not have to be very large, and it should retain setting reliably. With the distance measuring device, it measures how far the battery has traveled, turns off the motor, and you can apply the brake. The stop switch should be is actuated by the distance measuring device. It may be the same as the start switch. It turns off the motor to stop the buggy, and it could be used to apply a brake of some sort. For the wires, almost any type of wire can be used. Don't use too large of a size. Stranded wire will flex more before breaking, and solid wire holds its shape better. For better reliability, you should try to solder all connections so they don't fall apart. So for braking, all methods must involve either disconnecting the transmission or stopping or turning off the drive motor. So there's a couple of different braking methods. One is just no braking method. It's kind of like coasting to a stop, and it's called the Prairie method of braking. It's easy to implement, but the distance is very unreliable. The next one is mechanical types, and they tend to be actually easier to make. One is called the string and axle. There's another called the wheel jam, and a wing nut and axle, which is by far the most popular. The best combination is to have the wing nut not only lock the wheels, but simultaneously turn off the motor with a mini lever disconnect switch. And you can watch the video right there. And finally, it's electrical type, where it uses a drive motor as the brake. It works best in direct drive transmission. A DC motor provides some dynamic braking, and its terminals are shorted together. So some final suggestions is to think light. You should have the battery buggy as light as possible, so it doesn't need that much torque. You should design and build early, you should do a lot of calibrations, and be as consistent as possible. Practice at many different track lengths, and keep a record of the data. Try different batteries and motors, and a very important part is to calibrate. So make sure it goes straight. Those 20 points could make a big difference. So you can use alignment tools to help here, and you have to think about things such as would you use 2 sets of batteries for 2 runs. So let's go to some examples. So this is the first design of a battery buggy, which is a very common design. So what you have here is a motor connected to both a micro switch, a power switch, and a battery pack. So when the micro switch is not on, so there's going to be a axle here, by the way, with a wing nut on. So it's connected to the normally closed and the ground. So when you turn the power switch on, the motor will keep turning, and also the wing nut will go forward. So once this wing nut hits the micro switch, it'll cut off the power to the motor, stopping the battery buggy. The next one is something called a wheel jam. So this is an example from a scrambler. However, this is very bad for battery buggies, since when you jam the wheels, the motor still wants to keep turning, so you might damage the motor and or any of the other electrical components. The next one is a construction violation this year. This involves having the braking system contact the floor in order to introduce friction and therefore stopping the car. And this is a construction violation this year, so don't do that. So let's go to some pictures. So this shows an okay design from quite a while ago. You can see that they used a azimuth right here to keep track of the revolutions, which is very good. However, I don't know about these batteries hanging off the sides. It could be for weight distribution, but it looks like overall it is good design. Next one is another design. So you can see all the wiring is okay except for this giant amount of glue here. However, a very bad idea is to use a wheel that does not have a lot of traction, such as metal wheels. You should always opt for wheels that have traction so you can go faster and more reliably. The next one is from our own school a couple of years back. You can see they did use a 3-wheel system which was not very consistent, and that resulted in a bad placing for them. You can see they did use a wing nut and microswitch with a quite a good gear transmission. Next one is quite a good design. You can see that it has quite good wheels right here. The motor is correctly geared, and you can see overall it holds its structure very well, and most of the wiring is also very adequate. So the next one is something probably to avoid. You can see just a blob of wires and just pretty much it's held together by some sort of glue or something. So this is not that good for tournaments and stuff. You can see it literally looks like it's going to break apart, and most of the wiring is not good enough for a national level. So this is at the national tournament. And also the markings on this wheel are just very bad. So try not to do something like this. Try to make everything neat and simple so you can have a good battery buggy that travels the best. Okay, so that's it. I hope you enjoyed this presentation, and if you have any questions, just feel free to comment below.